Okay, let's start. Good morning, everyone. Today is April the 17th. Welcome to the IME 470 online class. Today we will continue lecture number 10, the network optimization one, which is about formulations on the shortest path. Let me first stop my video and share the screen. Okay, and let me see, annotate here. Oh, can I single page? Yes. Okay, so in the last class, we mentioned about the formulations of the shortest path. So the basic point is for node S, which is the source node, there exists exactly one outflow. So we should have sigma of all the out neighbors from S should be equal to 1, indicating there's only one unit of the outflow. For T, it is the opposite case, that any in neighbors, which means any nodes that from any nodes that can get to T, the summation of them should be equal to 1, meaning the inflow equal to 1 unit. And for all other nodes, which are intermediate nodes, we must have inflow equal to outflow, that if it is in the shortest path, then the inflow equals to outflow equal to 0. If it is not in the shortest path, then it's going to be inflow equals to outflow equals to 1. So, and finally, we have, of course, all xij's are binary variables for any ij in the arc. A is, again, the arc set, okay? Today, we're going to introduce another application of shortest path problem, which is decision making. It is very, very common in something like business strategies, or let's say this example is buy and sell maintenance decision strategy. So the problem description is as follows. A new car is purchased at 25,000 and at time 0, let's say. And the cost of maintenance and the resale value of the car is showed in this table, depends on the age. Of course, the older the car is, the cheaper reselling price it is. For example, after 5 years, in the beginning you purchase the car in the 25,000. In the end of the 5 years, or in the beginning of the 6th years, it is worth only 8,000. So to simplify the problem, we assume that it costs 25,000. The car price is going to be, unchanged, fixed. The goal is to minimize the net cost incurred during the next K years, let's say 5 years. I chose 5 mainly because I know most students will graduate in 4 to 5 years. That's why this is kind of like something as a plan to minimize your net cost about the car, let's say during the whole undergrad. Suppose you just, let's say, enrolled to NDSU, for example. And we can see something here. First of all, we need to assume two things. That first, we need to assume that at any time during the next K years, we must have a car. Otherwise, to be honest, the optimal solution could be without owning a car. And that's absolutely true. Before I have a car, I always dreamed of owning a car. After having a car, it becomes kind of like a burden because maintenance, repairing, all these kind of things. That if you just take Uber or take a bus, which is going to be easier actually, especially in big cities, you definitely don't want to, join the very, very high volume of the traffic and waiting for huge amounts of time. And also not to mention, let's say the gasoline cost and also maintenance, repair, this kind of things to have a car. Probably in big cities, you just want to take a bus, which is much, much easier. But here, let's assume that we must have a car during the next K years. After all, we're in Fargo, not a big city. The bus system may be not that advanced. So, and the second thing is that to avoid high maintenance of an old car, we can sell and purchase a new car. And there is also the strategy. I don't know, let's say how frequently you or your parents may, buy, sell, buy, sell. But in terms of the profit, or in terms of, let's say, the net cost, this is not a bad strategy. It depends, of course, what type of cars that you own. most of you may know that most Japanese cars are reliable and have very, very high resale value. Let's say Honda, Toyota, Lexus, but relatively some other cars may not have so much resale value. So maybe a better price, a better strategy maybe to buy a relatively new car and sell it in a relatively short time, and then buy, sell, you know what I mean? Although yes, you're gonna cost this kind of resale loss, you're gonna have the resale loss, but at least you can save the annual maintenance cost, and also your risk is lower in case there are big, this kind of mechanical problems. So this is another strategy. So we want to run an optimization model to automatically tell us which strategy is the best in terms of minimizing the net cost incurred. And again, to simplify the model, I assume that all trades purchases can only happen in the beginning of a year. In the slides that you have downloaded already, it may show that here it is by the end of the year. It's the same, you know what I mean? Let's say by the end of the 0th year is equivalent to in the beginning of the first year. By the end of the first year means at the beginning of the second year. So they are the same. Okay. First, I will wait several seconds here. Please think about it. How would you, the rough direction, how would you handle this model? How would you set up the model? Oops. Any ideas here? Again, if you want to say something, please unmute yourself. Otherwise, I cannot hear. Okay, let's introduce it, which is actually in the next slide. So here, because we assume that k equals to 5, in other words, I want to minimize the net cost incurred during the next 5 years. So we assume everything's in the beginning of the year. So in other words, I want to minimize the cost incurred at the beginning of the 6th year, because in the end of the 5th year is equivalent to at the beginning of the 6th year. In other words, I can build such a system and create a shortest path problem. How would it be working? Think about this. In the beginning of the first year, okay, then I have a cost, which is Cij here. Cij means the cost, the net cost, if we purchase a car in the beginning of the ith year, I'm talking about here, in the beginning of the ith year, and keep it until the beginning of the jth year. So for example, C23 means I will purchase a new car in the beginning of the 2nd year and sell it in the beginning of the 3rd year, which means, I just keep it for 1 year. And C, for example, 26 means I'm gonna purchase a new car at the beginning of the 2nd at the beginning of the 2nd year, excuse me, and sell it at the beginning of the 6th year. So this is my cost, or you can say my loss. And then once I have all of these Cijs, isn't it the equivalent, isn't it the problem of finding the shortest path from year 1 to year 6? Get the point? In other words, here's your S node and here's your T node. This is very, very important, a very important way of thinking of the problem. Let me repeat it again. It's really, really important. Okay. The original problem is to ask you to, let me clear. The original problem is to ask you to find a strategy to minimize the total, to minimize the net cost incurred during the 6th year, during the next 5 years, right? Okay, it might be a bit, more difficult for us to directly handle the problem, let's say algebraically. However, if we think about it using this way, in other words, I actually created a network, then it's going to be easier. Why? Because each of these Cij kind of like represent for your strategy, your action, right? Because once you have a Cij, you know what's going to cost. If I start from node I, start purchasing a new car from node I, in the beginning of, let's say, the ith year and sell it at the beginning of the jth year. And of course, since we assumed that at any time we must have a car, this tells me what? This tells me once I sell a car, I must immediately purchase a car. Unless it is the 6th year, that, after the 6th year, I don't care. As long as, in these intermediate nodes, intermediate years, if I sell a car, then I must purchase a car. That's very clear. Okay, in this case, I'm gonna equivalently solve an shortest path problem instead of this, complex business strategy or decision-making problem. They're equivalent. Okay, so once I know all these CIJs, I know it is a shortest path problem, and I know I can use methods, for example, Dijkstra's algorithm, this kind of DP algorithm to solve it. Now the problem is, how can you really formulate it to a shortest path problem in detail? In other words, I'm asking, how do you get all these CIJs? Okay, first of all, as usual, we define, corresponding to Cij, we define an Xij as a binary variable that if Xij equal to 1, and then if Xij equal to 1, we mean that we're gonna purchase a new car in the beginning of the ith year and keep it till the beginning of the jth year. Xij equal to 0, that means no, I'm not gonna do this. Of course, by keeping it, you have to pay for the maintenance fee. Again, I copy and paste the table here. Okay, so for example, this means if the age of the car is 1 year, the maintenance fee is 3,000, 2 years, 4,000, 5 years, 7,000. I think it's too much, isn't it? I don't know how about your cars, but I don't think I pay so much maintenance fee for my car. Anyway, I guess this data includes a lot of things, not only maintenance, let's say expectation of the repairing, and also, let's say, gasoline cannot be included. Gasoline included is too cheap. Well, assuming this data is correct, and the resale price, your annual maintenance fee is increasing, but your resale price is decreasing. So for sure, there's a balance that you should, there's a balance point, or you can say a marginal, no matter you say loss or profit, it doesn't matter. At some point, you're gonna sell it. And we want to find what is this exact point. And don't forget that time t is not go to infinitive. It is to 6. So you have to think about your last strategy as well. Why? Because after the after 5 years, or let's say in the beginning of the 6th year, you no longer have to own a car. You can simply sell it. Okay, now let's have a look. Let me ask you a question, very simple. What if I purchase a car, new car, in the beginning of the first year, and then I sell it in the beginning of the 2nd year? How much will it cost? What I mean is that how much would you totally pay? If I buy a car in the beginning of the 1st year and sell it in the beginning of the 2nd year. You see, first of all, what is your cost? Your cost is the 25,000. Let me write this in the Excel. Come on, smaller. Where's my Excel? It's here. Okay, let's see here. C12, meaning again that I'm gonna buy a car in the beginning of the 1st year and sell it at the beginning of 2nd year. So this simply equals to 25, which is your cost for purchasing a new car, right? And then because you keep the car for 1 year, your maintenance cost is 3,000, of course. And then by the beginning of the 2nd year, or by the end of the 1st year, you're gonna sell the car. Then it's gonna be 20, minus 20. So you cost 25 plus $3,000, and you get 20,000 back. So totally, your cost is 8,000, right? Okay. Now let's have a look. What if, let's say, I purchase a car in the beginning of the 2nd year, and I sell the car in the beginning of the 3rd year? Similar. In the beginning of the 2nd year, what is your cost? 25,000, and you're gonna keep the car for 1 year. So you're gonna cost $3,000 for the maintenance, and then you're gonna sell the car, from which you can get 20,000 back. So exactly the same. Oops, why is different? Oh, okay, minus 20,000. So exactly the same. It's gonna cost you 8,000, and do the same for whatever. As long as you purchase a car in the beginning of the ith year and you sell it in the beginning of the I+1 year. Let me make it a bit more strict. Let me add two brackets here. As long as you do this, for sure, in the beginning you're gonna cost 25,000 for purchasing a new car, and because you keep it for 1 year, it's gonna cost you 3,000 for the maintenance, and then it's gonna you're gonna get 20,000 back because you sell the car. So no matter what is the I from 1 to 5, Ci I+1 must be equal to 8. Clear? Any questions here? Simply because here means the age of the car. Okay. Now let's have a look at the second case. How about I buy a car in the beginning of the first year and I sell it in the beginning of the third year, which means from here to here. How to think about it? Let's do the same. Do it by the same way. First, what is my total cost? 25,000 at the beginning to purchase a new car, and then because I buy it at the beginning of the first year and sell it at the beginning of the third year, in other words, I have kept it for 2 years, right? So what is the maintenance fee of the 2 years? It is 3,000 for the first year and 4,000 for the second year. So your total cost is 25 plus 3 plus 4. And then how much you're gonna get? When you sell the car, you're gonna get 18,000 back, minus 18,000. In other words, it's gonna cost you $14,000 for doing so. And then let's see, the same. Suppose I purchase a car in the beginning of the second year, and I sell the car in the beginning of the fourth year. What's gonna happen? Isn't it exactly the same? Because you keep the car for 2 years. It doesn't matter which year you started purchasing a new car, purchasing it as a new car, but you keep it for 2 years. So to keep it for 2 years, you have to pay for 7,000 for the maintenance, and the resale price for a 2-year-old car is going to be 18,000. So if that's the case, it's going to be the same: 25,000 plus 3 plus 4 minus 18,000. And of course, it's again 14. And using the same way, you're gonna see no matter what is this I from 1 to 4, you're purchasing a new car at the beginning of the ith year, and you sell. Oh, sorry, I plus 2, not I plus 1. And you sell it at the beginning of the I+2 year. Your total cost would forever be in this way: 25 minus 3 minus 4 plus 3 plus 4 minus 18 equal to 14. Okay. And then exactly the same, what if I purchase a new car in the beginning of the first year and I sell it in the beginning of the fourth year? What's gonna happen? Similar, right? You're gonna pay 25,000 for the purchase, and then you're gonna keep it for 3 years. So you're gonna plus 3 plus 4 plus 5.5, and how much you can get back when you sell the car? $15,000, and it's gonna cost you 22.5 thousand. 22. Oh, that's a lot actually. Seriously, 22.5 thousand. That's close to the selling price. That's close to the new purchase price. So here I plus 3. Why this I is capital I? Don't understand. Auto correction must be. That's gonna be the same, right? That's gonna be 25, and to keep it for 3 years, 3 plus 4 plus 5.5, and then you're gonna sell it at 15,000 minus 15, so it's gonna be in this. Similarly, with C15, you purchase it in the beginning of the first year, plus the maintenance fee of the 4 years, because you're gonna keep it for 4 years. You're gonna sell it at the beginning of the 5th year. Then you're gonna pay for all these maintenances maintenance fees plus 3 plus 4. Oh, that's a lot indeed. Plus 5.5 plus 6. How much you can sell? You can sell at $10,000. Interesting. See what? This is already more than purchasing a new car. And similarly, you're gonna have what? You're gonna have you purchase any car from the beginning of the ith year and sell it at the beginning of the I plus fourth year. Similar, right? You're gonna pay for so much. 25 plus 3 plus 4 plus 5.5 plus 6 minus 10 equal to 35.5. It's 33.5. Okay, and then the last column, make it a bit bigger. And then if you just see I6, this is only 1. You don't have I plus 1 anymore because your I can only be 6. This equal to what? Similar. I'm gonna purchase at 25,000 and I'm gonna pay for all this maintenance fee. This is clearly not a smart idea because the maintenance fee is really too much. Plus 7, and to sell the car, I can only get 8,000 back. Whoa, 42.5. That's really huge. Okay, so that I have all these C's, see it? 4 and 5. Let me make it to the red color. I have all these C's. Now it's a time for us to. Now it's a time for us to really apply it. How to apply? So Ci I plus 1 equal to 8. So that means C12, C23, C34, C45, C56 equal to 8. And you can clearly see all these C's here are indeed equal to 8. 3, 4, 5. Okay, so next, Ci I plus 1 equal to 4. Similarly, that means C13, C2, where there's 2, 4, and C3, 5, C4, I cannot find it. Where's C4, 6? Did I miss it maybe? Anyway, let me clear all of this. C4, 6 is here, C4, 6. All of these equal to 14. And Ci I plus 3 equals to 25. That means C14, it is here. C14, C25, C36, these are equal to 22.5. And Ci I plus 4, that means C15, C26, these two equal to 33 plus 33 plus 5. And the last one is C16. The last one is C16. Here we go. C16 equal to 42.5. Where's the C16? Here we go. Okay. So in this case, yes, I have found all these numbers. Total how many? 5 plus 4 plus 3 plus 1 plus 2. Anyway, 5 sum from 1 to 5. Okay, sum from 1 to 5 equal to what? 5 times 6 divided by 2 equal to 15. So I have all these 15 Cij numbers. Now I have all the Cij. How to calculate it? Shortest path problem, right? I want to go from 1 to 6. What is the shortest path? Which is equivalent to ask what is the minimum total cost. Okay, and then you can easily solve it. Get a point? I guess the shortest path is like this. You get 314 is the shortest. Why? Because you have by 314 it is the last for 2 years, right? 2 years you lose 14,000. That means per year on average you lose only 7. And this is 8. If you go this way, it is 7.5. See it? And if you go this way, that's 8 point something. So you must go something like this: 1, 2, 3, 3 to 4, 3 to 5, and then 5 to 6. Yeah, this should be the optimal solution. Let me think about that. If that is the case, let's see. Wait. Is it possible you go? Maybe you can go this way. From 1 directly to 4 cost you 22.5, and then from 4 to 6 cost you 14. So in this case, your total cost is 36.5. If you use the first strategy, it's a 14 plus 14 plus 8, which is 30. It's still it is still better. In this way, you cost only 36. Then yes, the best way is 1, 2, 3, 3, 2, 5, and 5, 2, 6. So in this case, your total cost will be 36. And indeed, this is the shortest path to solve this problem. Okay, so here we've seen an example of using shortest path. Okay, of using the shortest path to do business strategy. Any questions here? And then, by the way, this is a very popular way. In many cases, of course, you're not gonna do this by your hand. You're gonna use computer to really, do it. So you're gonna actually code it. The most important thing of this example is the idea of modeling, because the computer cannot help you model. The computer can just help you calculate something. But modeling is your business, at least now. I mean, I don't know after 50, 100 years what's going to happen. Maybe computers will be smart enough to model the problem, but at least currently they cannot. And I don't believe in 10 or 20 years, computers going to be smart enough to directly model the problems. I don't believe it. So this is the most important thing. Later, I hope you can realize or you can recall that shortest path has a function like this. In many this type of business strategy problems, you can use the shortest path to model. If we make it a bit more general, the case is what? The case is, again, have a look here. All these are what? Are stage-based. See it? Stage-based, and you can have something like a recursive formula as the CIJs here. Again, that reminds you what? Dynamic programming, right? The principle of dynamic programming, that it's stage-based, and then you have a recursive formula. Remember, I'm talking about this. Let me go to lecture 9, open the DP. Where's the DP? Let me see. It's here. Okay, so I'm talking about this. Stage-based and the recursive formula. The solution to the next stage only depends on the solution to the current stage. And how about here? Very similar. The solution from 3 to 6 depends on the solution from 1 to 3. See it? And the stage-based is very clear because totally you have 6 years. I mean, totally you have 5 years. You're gonna totally own the car for 5 years, right? And in this case, shortest path or more generalized DP. Okay, so this is very popular from industry to even the research level, because the research problems usually are a bit more difficult, more theoretical. Actually, even for research problems, yes, we do use DP. And personally, DP is my favorite, really my favorite algorithm or methodology. That's not just a method, it's a methodology, a great methodology. So it shows you the power. And later, if you have a time, you have a chance to do some, let's say graph theory problems, let's say traveling salesman problem or vehicle routing problem, these types of problems, you're gonna see DP are widely used. Or if you have a chance to go to industry, especially this kind of, working for business solutions, and then also many problems are similar, not the same, are similar to this. Of course, the real problems, you won't have only 5 stages. You may have 5,000 stages. You won't have only 2 parameters, which are the annual maintenance and the resale price. You may have, let's say, 200 parameters, but the same. What you need to do is just to write a for loop in any coding language and let the computer do it rather you do it by yourself. But the idea would be exactly the same. Okay, it's really important. And finally, of course, how to interpret a solution here, because it's very simple. We observe it by our eyes. But what if, suppose, say I change the data here and I also make the year of the car to be, let's say, 50 years. Or let's say I add more features. Features means more parameters, this kind of variables to be considered. And then it may not be that easy for you to use your eyes to get the solution. Then we run the solver from a computer and then we get a solution. For example, the solution is 1, 2, 3, 3, 2, 5, 5, 2, 6, for example. How to interpret it? So this means, suppose this is a solution. 1 to 3, 3 to 5, 5 to 6. This means I'm gonna buy a new car in the beginning of the first year, and then I'm gonna sell it in the beginning of the third year. And then meanwhile, I'm gonna purchase another new car costing me $25,000, and then I keep it till the end of, till the beginning of the fifth year, and then I purchase again a new car, and then keep it till the beginning of the sixth year. So this case is my interpretation, okay? And the total, as we mentioned before, you're gonna cost how much? 14 plus 14. And yeah, let me see. Yes, 14 plus 14 plus this is 8. So totally you're gonna cost $36,000. And that's everything. As an exercise, please solve the problem by Dijkstra's algorithm and then formulate the IP and solve it by Excel. This is, very, very similar to the formulations here. As long as you make it to be the shortest path, it's really simple. You can formulate something like this way. This is even more difficult. This problem is more difficult, much more difficult than this problem, okay? So, and then for fun, you can consider the real strategy for your own car in real life. Or for example, you can ask your parents, for example, if you don't have a car so far, you can ask your parents for the data. Let's say on average, how much will they cost, let's say annually with the respect to the age of the vehicle. And then for the resale price, well, to get KBB, okay, Kelly Blue Book. And then you can really have a new model. By the way, I don't know how many of you are very interested in cars. Have you heard of a website called, what's the name? Car Guru, I think. Car Gurus. Let me see here. Have you heard of this one? This website? Now there are a lot of similar websites, but as far as I know, this is one of the very first website calculate what the solution for you about not really the solution like so complete like this way. So what I mean, a solution is the fair price of the vehicle, and it's not like a KBB. KBB just to give you the price, just the price itself. But for this website, it gives you not only the price, but also for not only the price for this model, but the price for kind of like cars. For example, let's choose this car, and it's gonna tell you it's a great deal, and it's below the market 6642. Question is, how did they calculate this number? Because this number is kind of like for specific cars. And you have to consider many, many different factors. Let's say, what is the trim, brand name of the car, how many miles, and the maintenance, a lot of different things. And you may not believe that's similar using this type of problem, using this type of models, but it's going to be more complicated. I personally believe, and guess, I should say, I personally guess they use more statistics than simply use this kind of integer program problems. However, similar, they must have they must have decision-making strategy. And finally, they're gonna give you a number, or let's say a range. The range will be somewhat like using hypothesis testing or confidence interval, and this number will be probably the mean value of that, and then use the listed price minus that one. All these are what are kind of like a business strategy, and you know how much they earn. I don't know which year this one opened, probably within 10 years, because I remember before I had never seen it. And until one day, at that time I was still a student, I saw it and I feel really so impressed because I've never seen, let's say, give you a price and immediately give you this and give you this range. Great. And immediately this website got huge amounts of money, fundings, but the basic knowledge is what? As similar to all these kind of business strategies and the statistics, not necessarily this shortest path, I may use strategies. So important thing is what? Important thing is you have the basic knowledge plus some observation of the world that you think which idea would greatly apply to the world. And the foreign idea is not, may not be that useful if you just have the idea itself. You may have some knowledge to make the idea come true, right? That's what do you need to be successful? First is to have some knowledge. And second, the most important thing is to think. Think about the world rather than just completely accept. Because by thinking, you may find something is not done, and that's a chance, great opportunity for you to make it better. And meanwhile, you can be, successful in terms of no matter achievement or fortune. Okay, that's everything about lecture 10, about the formulations and more a bit, about the applications of the about the shortest path. Any questions here? No question? Okay. Then let's go to lecture number 11. I realized one thing, that online teaching is really fast, much faster than my plan. Main reason is because come on, single page. Okay. Main reason because I guess because we're online, we cannot see each other face to face, so that not so many students having questions, or let's say or provide some different ideas. This is both good and bad. Mostly it's bad, I'm afraid, negative. You are strongly recommended, again, having the same routine as you had, regularly, so that you can keep your study efficient and keep yourself running. Always push yourself ahead. Otherwise, staying at home, it's gonna be not that positive, because everybody might have a tendency to be kind of a bit lazy or something. It's really really important to keep the routine. Okay, anyway, let's start 11, lecture 11. Lecture 11 is the second topic of network optimization. It is another program called the minimum spanning tree program. So in the beginning of the lecture, let me first define some terms. First of all, we assume that in this lecture, all graphs are undirected. Undirected, what I mean is that for any two nodes, let's say I and j, if ij is an edge, then ji must be an edge. In other words, all these, if you consider it as a traffic, so all these kind of streets or roads are undirected, let's say bidirected. There's no, let's say, one way. All of them are two ways. If you can go from A to B, then you can go from B to A as well. And in this case, we replace previous notation, which is A arc set by E. E here means edge set. When we say edge, that means it's undirected. That is two ways. When we say arc, then you need to be careful, because it's possible there's a one way, like the University Boulevard, out of the campus, just next to the campus. You can only go from the north to the south. You cannot go from south to the north. Otherwise, you're gonna get a ticket. That's serious. So here we assume all graphs are undirected in this lecture. And the next one is the concept of connected graph. If a graph is connected, that means any two nodes in the graph are connected. In other words, for any two nodes, there exists a path to connect them. For example, consider this graph. This graph is connected. Why? Because any two nodes, they have a path to connect them. For example, 6 to 5, I can go from 6 to 1, 1 to 3, 3 to 5, connected. 2 to 3, for example, 2 to 4, 4 to 5, 5 to 3. And you can have any two nodes, there's a path. This graph is not connected. Why? Simply because from 1 to 4, for example, you cannot go. How can you go from 1 to 4? There's no way. For example, because these two parts are not connected. See it? So this graph is not connected. And the next term is tree. This is a tree in the life, of course, very popular. Everybody knows what is a tree. But if you carefully observe the tree, you're gonna see what? You're gonna see first, any two nodes in the tree are connected. Otherwise, for example, there's something, a leaf here. Otherwise, it's gonna fall. It's gonna be, away from the tree. If there's a tree, no matter how small the branches are, all of them must be connected. In other words, in terms of the graph theory, a tree must be a connected graph. And the second thing is acyclic. Acyclic means the graph does not have any cycle. So for example, this graph, first of all, of course, they're connected. That means between any two nodes, there is a path, but it's cyclic. Why? For example, you can go to 1, 2, 3, 1, 2, 2, 2, 2, 3, 3, 2, 1 again. You go back. And this one, similar. That's cyclic. 6 to 1, 1 to 4, 4 to 2, 2 to 6. You can go back, right? However, this one is acyclic. Why? For example, you can go from 1 to 5, 1 to 2, 2 to 5. Can you go back from another path? You cannot go back, along the same path. No, you cannot. There's only one path from 1 to 5. See it? Sorry, I should have not. Yes, that's correct. There's only one path. You can only go from 1 to 5 along 1 to 2, 2 to 5, this path. You don't have another, let's say, for example, suppose there's a way like this way. Suppose there's an edge directly from 1 to 5. Then clearly it's cyclic. Why? Because 1 to 2, 2 to 5, 5 to 1. It is a cycle. However, here we do not have this link, so that it's acyclic here. For any two nodes, they are connected, but they are not cyclic. Okay, so in this case, yes, this graph, it is a tree. Indeed, it's a tree. But this is not a tree. Although it's connected, it's not cyclic. Although it's connected, it is not acyclic. It is cyclic. This is also not a tree. Why? Because although it is acyclic, it's even not connected. For example, from 1 you cannot go to 4. Again, it's a tree if and only if it's connected and acyclic. Okay, in the next slide, let's see more examples. For example, this is a tree. And for this type of tree, we have a special name called a binary tree. I don't know, have you heard about it in any this kind of computer science classes? This is mostly used in computer science, a binary tree, which is yes or no, or 0, 1. And the computer is made up, computer theory is made up of this kind of binary trees or binary decisions. So that, for example, from each node, you have only 2 child nodes. This is called a parent node, and these are called child node. For each node, they have at most 2. You can have 0, which means it's a leaf, as a leaf of a tree. Or you can have 1 as the only child node, but you can not have more than 2 nodes. So it's a binary tree. Of course, you can use the previous. Definition to see it. For example, it is what? What happened here? For example, it is connected. Yes, of course. Any 2 nodes, there's a path, and it's acyclic. You cannot find any cycle here, right? And how about this? This is also a tree, okay? Similar, but this is not a binary tree because, for example, consider this node. It has 3 child nodes. It has 3 children here rather than 2. First of all, again, all of them are connected. And the second, it's acyclic. You cannot find a circle. See? Can you find a circle in this graph? No way, right? But how about this? This is not a tree. Be careful. Why? Because it's cyclic. 1 to 2, 2 to 5, 5 to 3, 4, 4 to 3, 3 to 1. See it? You go this way, you go back. It's cyclic, so this is not a tree. How about this one? It's a bit more complicated, but similar to this one, right? Just a larger version of this one. This is also a tree. And in the real life, a tree could be billion-wise. Why? Consider, for example, Facebook, LinkedIn. You get a point? If there's a node between A and B, then I give them a link. However, sorry, the previous claim is something wrong. I cannot say it's a tree because it could be a cyclic. Let's say A knows B, B knows C, C knows A. That's it's gonna be back. And later for that types of the graphs, we're gonna apply the idea of spanning tree and a minimum spanning tree. But I should say this: the graph. I cannot claim it's a tree. The graph in our real world could be billion-wise, huge. Consider, let's say, again, Facebook, LinkedIn, this kind of things. You know the recommendation system, right? Nowadays, it's a super hot topic. Recommendation system, no matter, let's say, for a friend recommendation, let's say you open your Facebook, you're gonna see, hey, there's a you may know, B, you may know. Interesting. Why? How did the algorithm find it for me? Why the algorithm recommend this guy for me? And in many cases, it's pretty good. It's pretty accurate. What is the principle behind it? Something like this. You want to generate a relationship because suppose let's say you and another person, let's say X. If you and X have many common friends, and if these common friends do have a cycle, it's not a cyclic, it's cyclic, then you know what? Probably you know X, right? Because you have so many common friends, and this common friends itself makes a group. Then the system may recommend X to you. The question is, think about this: how many people in the world? There are more than 77. How many people? I think approximately 7.5 billion. It's our current population. How would the system really find all this? First of all, for example, they can search with respect to your area, the region, or with respect to, for example, your companies or let's say schools. So say, for example, suppose people are working in or studied before in NDSU, and in which year, if you have some common years together in NDSU, then the system may recommend, set these people as a priority to recommend them to you. And the second thing is also something like, for example, hometown. For example, although I didn't study in NDSU, but I've been living in Fargo for example, 20 years, and another one also lived in Fargo for, let's say, 15 years, and after he or she went to another university, then very possible when both of you were kids, you know each other, and also they're going to recommend in this way. So there are a lot of this kind of theories behind this kind of applications about the recommendation system. And also something, let's say YouTube. You're gonna see YouTube nowadays, they always recommend some videos to you. For example, suppose you like, for example, linear programming, and then you open the YouTube, you're gonna see a lot of this kind of lectures or something about linear programming. Suppose you like, let's say, sports, then you open the YouTube, it has a lot of such, related videos. The problem again is how did the YouTube know your preference? How did the algorithm behind it working? Similar, in many cases, they use graph theory, or they use some statistical learning, or in general, let's say machine learning, this kind of algorithms. And if we have more chance, we may discuss it a little bit more. But this tree structure here, is everything clear? By the way, this is a picture I took by myself. It was in San Diego. Today, due to the time limit, I don't have enough time to show you. In the next time, if I forget, please remind me in the beginning of the next class. I'm going to show you where it is, exactly in the Google map. And later, if you have a chance to go to San Diego, that specific point, please remember to also take a picture of this, and you can also upload it to Google. It's going to be really fun. This tree is so beautiful. Anyway, okay, so today is about the end due to the time limit. That's everything about today's class. And by the way, please remember to start the homework as soon as possible, because I realize there's a problem that many students send me email in, let's say, by the end of Thursday or on Friday, and that is kind of like too close to the due date, right? You're highly recommended to start the homework ASAP, so that if you have any questions, you can ask me during, let's say, the office hours, or at least a bit earlier than the due time. That's gonna, make it safer. Because what if, for example, I didn't see the email or I reply later, then you may not, be able to submit the homework on time. We will have one more homework, so homework number 6. And after homework 6, I think it's gonna be finished. So we will have one more lecture. After lecture 11, we will have a lecture 12 talking about the third topic about network optimization. And after it, it's gonna be everything. Okay, thank you very much for the class today. Have a good weekend and see you on Friday. Sorry, see you on Monday. Bye-bye.